In this video, we'll be talking about the components of a vector. Now, there are two components. Again, there are two details, the magnitude and the direction, but there are also two components to every vector. Two components to every vector are the x direction distance and the y direction distance. This right here is the notation of how we'll generally define a vector. So this vector v in this case is defined as -4 units in the x direction and 7 units in the y direction, such that we've started at the origin. Again, the concept of this is that this provides us the x distance and the y distance. Now, what's important here is I did specify that it was starting at the origin. It doesn't have to start at the origin. It can start anywhere that I want as long as the initial point starts somewhere and the terminal point is 4 units in the negative direction of x and 7 units in the positive direction of y. So if I were to draw this vector v right here first on this coordinate plane, you'll notice that I'm going to start my initial point at the origin, 0, 0, and I will go -4 units x, 1, 2, 3, 4, and I'll go positive units 7, 1, 2, 3, 4, 5, 6, 7, so about here, which means that this vector really is from this point here to this point here. So when I draw that in there, again, it should be a straight line, that's my vector v. Now, sometimes I'll denote vector v as v, sometimes I'll denote it as a v with an arrow on top of it. It's important to understand that this is the same thing as this vector v up here. Again, in this case, I've made it bold. Sometimes you'll see it capital. Sometimes you'll see it v with a little arrow on top of it. Those are all the same thing. They're just defining it as a vector. So again, the vector -4, 7, -4, 7 looks like this. Also notice that they're using brackets. Sorry, I should be more poignant about this. They're using the greater than, less than symbols as the brackets of a vector. So we have parentheses, which generally coordinate to a point. We have squiggly brackets, which coordinates to a set. Now we have these diagonal brackets, which specifically focus on a vector. So let's go ahead and look at this next example where it says use the grid below to draw the vector between 2 points. So let's go ahead and draw these 2 points in here first. So I'm going to go 2, -1, so right about there. And I'm going to go -2, +6. 1, 2, 3, 4, 5, 6. And then I'm going to connect those 2 points. So when I connect those 2 points there, you'll see that vector. Now, hopefully, by looking at this, it says, explain how the two vectors are related. Well, this vector is v. What is this vector? Well, it's important to note that this vector is defined by moving 4 units to the negative side from its initial point, and then 7 units positive in the y direction. If I do that with this vector, 1, 2, 3, 4, and then 1, 2, 3, 4, 5, 6, 7, you'll notice that this actually has the exact same identification as v, the vector v. So how do we explain or how the two vectors related? They're not actually different. Because again, remember, a vector is defined by 2 things. And I'm going to go ahead and start dividing it here. The magnitude of the vector and the angle or the direction of the vector. So those are the 2 key qualities of a vector that makes it unique. In which case, these 2 vectors are not unique. They are inherently the exact same vector. So how do we determine what the magnitude is? Well, the magnitude is nothing more than the length of this line. Well, if we understand that the length of this line can be simply put as the hypotenuse of a triangle, well then it's just the distance of this, which if this distance is a and this distance is b, again the x value of the coordinate system and the b value of the coordinate system, then our vector for, then the length of this vector or the magnitude of this vector is nothing more than this little notation down here, where we have, again, it looks like an absolute value, but it's a double set of absolute value bars. The reason why we're using that double set is specifically because we wanted to note that the interior thing is a vector, not a number. It's not the absolute value of something. It is the magnitude. Again, this notation here refers to magnitude of v. And that magnitude is the distance in x squared plus the distance in y squared inside of a square root. So if we were trying to find the magnitude of this, we'd simply take -4, square it, add it to +7, square it, and then square root it. That would give us, again, a squared plus b squared equals to this value of c squared. So that's where that rule for the magnitude is coming from. The distance or the direction in which we're talking about theta, that'll take a little bit more work for us to do, so we'll go ahead and do that in a separate video. Now, if we're talking about multiple vectors in terms of adding them or subtracting them, in the previous video we talked about, well, we could just simply tail to end the vectors together. Well, now we're talking about mathematically how do we actually attach them. Well, if I have a vector v that has a and b as its setup, and we have c and d for the w vector, well, if I'm adding these 2 vectors together, what's convenient is I'm simply adding the x coordinates and I'm adding the y coordinates. What if I've got a scalar attached to a vector? And again, that's what that k would represent. It's a multiple of the vector as a whole. Well, conveniently enough for this one, the mathematics for this is relatively straightforward. We simply multiply k into both of those pieces. In this case, it feels like you're distributing it. So, in example 8, we're looking at perform the given operations. V is equal to negative 2 comma 3 and W is equal to 4 comma negative 1. If I'm looking for the length of W, that means I want the length of W is equal to, and I'm going to go ahead and write this notation down so it's clear, 4 comma negative 1. This is the same exact notation. What I'm going to then end up doing is saying that this is the x-coordinate 4 squared plus the y-coordinate negative 1 squared, and I'm going to square root this. So 4 squared is 16, 16 plus, again, 1 squared is 1, so this is the square root of 17. That means the length of this vector is simply the square root of 17. If we're looking to add the two vectors, again, we're simply taking those two vectors, that's negative 2 comma 3, added to the vector 4 comma negative 1. And when I add these two vectors together, I'm doing nothing more than adding the x-coordinates, negative 2 plus 4, and adding the y-coordinates, 3 plus a negative 1. In doing so, I simplify those individual coordinate points. So negative 2 plus 4 is simply 2, and 3 plus a negative 1 is 2. So the vector such that W plus V, or V plus W, what's nice about vectors is they are commutative. You can add them in any order. When adding those two vectors, we simply get the vector 2 comma 2. In the same note, when we're looking at negative 3 times v, now remember the negative simply flips the direction on end, but that means it does change or affect its x and y coordinates. Well, if I'm looking at v remember is a negative 2 comma 3. If I want negative 3 times that, remember negative 3 now behaves as though it's a scalar. So when I multiply this, it's really negative 3 times the vector negative 2 comma 3. So when I'm actually multiplying this thing, I'm technically distributing this in. Again, that's mathematically what we are allowed to do with this, giving me then a negative 3 times a negative 2, comma, for the x-coordinate, and negative 3 times a positive 3 for the y-coordinate. This provides me then with a coordinate of 6, comma, negative 9. Now, to better understand what's actually happening here, it would be viable for us to draw this vector and see it on a coordinate plane, and then draw this vector and see it on a coordinate plane. Hopefully, seeing those two vectors together, you'd recognize that this one here is 1/3 of the length of this one, and this one is going in the opposite direction than this one is. And again, exact opposite, meaning 180-degree rotation, it's now facing the opposite direction. In completing letter D, you're simply doing all of those pieces but together. So I'm going to have 2 times my v, so negative 2 comma 3, multiplied by 2, the scalar, that 2 is going to distribute in, minus 3 times my w vector being 4 comma negative 1. So in combining these two vectors together with their scalars appropriately, the 2 is going to distribute into both these pieces, giving me negative 4 comma 6, minus, I'm going to distribute the 3 in, giving me 12 comma negative 3. And then I'm going to have to make sure that I'm subtracting these coordinates. Now again, technically with vector addition and subtraction, there is no real subtraction. It's really just adding the coordinate points with a negative distributed to the second term. But I'm going to go ahead and treat it this way. This is the same thing as negative 4 minus 12, comma, again it's minus 12 because it's minus that 12. And then I'm going to have my 6 here, minus a negative 3. So if I simplify this in its entirety, I get negative 16, comma, positive 9. And that will provide me with the actual vector that is 2v minus 3w. Again, just combining the terms in those coordinate locations.